Let us summarize what we have been discussing so far. We have been considering, without using the word postulates, we have been discussing many postulates of quantum mechanics. Now let us try to consolidate them. Okay. The first one is the idea of state ket. Corresponding to a physical system, there is a complex vector space. Every state of the system is represented by a ket or a ket vector in this vector space. Then next postulate is corresponding to the idea of operator. Every physical quantity is represented by a Hermitian operator that acts on the vector space of the system. And this Hermitian operator has different properties. Its eigenvalues are real. Eigenkets are orthogonal to mutually orthogonal, and the eigenkets form a complete set, so they can be used as a basis of this vector space. Okay, these related ideas are also there. The next postulate is about eigenvalues of the operator. The result of every individual measurement of a physical quantity on a state of the system is one of the eigenvalues of the operator corresponding to that physical quantity. Okay, we have seen examples also. We have discussed this in detail. Okay, the sequential Stern-Gerlach experiments provide a very good example. So the result of every individual measurement is one of the eigenvalues of the operator corresponding to that physical quantity. After the measurement, the general state of the system changes to the eigenstate corresponding to that eigenvalue. Suppose in a particular trial of measurement, we get an eigenvalue, let us say A5. Okay. Then after the measurement, the general state of the system undergoes a quantum jump, or it collapses to the eigenket corresponding to that eigenvalue A5. That is ket A5, we can say. Okay. So this is also a postulate in quantum mechanics, and all these, remember that all these postulates are deduced from empirical evidence, from experiments, actual experiments. The fourth postulate is about expectation value. And before we go to the definition of expectation value of an operator, let us first consider this. When the initial normalized state of the system is, let us say, ket alpha, then the probability of getting the eigenvalue A prime as the result of measuring the physical quantity capital A is bra vector A prime ket alpha mod square. That is the inner product between A prime and alpha, the square of that. That is the probability of getting A prime as the result of a measurement. We know that the result of an individual measurement is one of the eigenvalues of the operator A. What is the probability of getting a particular eigenvalue as the result of an individual measurement? That probability is given by this quantity, the inner product between A prime and alpha, square of that. Okay. This is actually the square of the inner product between A prime and alpha will be the expansion coefficient in the expansion of ket alpha in terms of the eigenkets of the operator A. So the square of the expansion coefficients gives you the probability of getting that particular eigenvalue. In other words, it is the probability of the system undergoing a quantum jump from a general state vector to an eigenstate of the operator. Okay. Now, once we have this probability, it's very easy to calculate the expectation value. Expectation value is the average of a large number of measurements of A in this state. Okay. Remember again, in order to get a large number of measurements of A, we need to use an ensemble of a pure ensemble of the system. Okay, so that we have a collection of identically prepared systems all in the same state, so we can do a large number of trials and then we take the average value, and this average value is given by the expectation value, and the equation is expectation value of A, the angular bracket is the notation for that, is bra vector alpha operator A ket alpha. Okay, and if either we expand this bra vector alpha and ket alpha in terms of the eigenkets of A, that is in terms of ket A prime, or we express the operator A itself in terms of its eigenkets, we can easily show the result that this expectation value is equal to sum over all eigenkets A prime, that is eigenvalue, times mod A prime alpha square. That quantity is the probability. So it is summation over A prime, summation over all eigenvalues, we can say, each eigenvalue multiplied by the probability of getting that eigenvalue. In other words, it is the sum over all data or all the measured values, okay, that the product of each value and multiplied by the probability of getting that value. This is the standard way of calculating the average of any data set. Okay, so it's clear that expectation value defined in this peculiar way, that is bra vector alpha, operator A, ket alpha, that readily gives you the weighted average of eigenvalues. Okay, that is the average of a large number of measurements. So we have considered these four postulates. There are related ideas, of course. Okay, corresponding to each postulate, we can bring in many related ideas. So basic postulates are these four so far that we have identified about how to define, how to represent state of a system by a ket in a complex vector space, how to represent a physical quantity by a Hermitian operator acting on that complex vector space. Then what is the result of measurement? What is when you measure a physical quantity in a state, what is the result of individual measurements? One of the eigenvalues of the operator. And what is the probability of getting a particular eigenvalue, okay, and what is the average of a large number of measurements, expectation value. And in this expectation value, actually these two statements are mutually dependent, okay, they are not independent. So if in some textbooks you can see the first part as the postulate, that is probability of getting a particular eigenvalue is that modulus A prime alpha square, that is given as a postulate. Then from that you can deduce the average value, expectation value you can deduce. In some books you can see expectation value is given as a postulate. Okay, so it is given as the average of a large number of measurements. Then if you expand this expectation value and you accept that expectation value is indeed the average of a large number of measurements, then there are the second term, that is sum over A prime times something square. You get something like that. Then it's clear that it is sum over all possible data points of each data point multiplied by something. Okay, then it's clear that that something must be the probability of getting that data point, probability of getting that eigenvalue. So if we start with the expectation value, the definition of expectation value as a postulate, then we can deduce the probability of getting any one eigenvalue. That is that mod square of inner product between A prime and alpha. So in some books probability is given as the postulate and then you can reduce expectation value. In some other books expectation value is given as postulate, from that you can reduce probability. Okay, that both are interdependent. From one you can reduce the other. So we have been considering these four postulates. Okay, we will add two more postulates, okay, to this set later. Okay, now what we are going to do is these ideas regarding the ideas in these four postulates we are going to illustrate using spin half system. Okay, for this we again go back to the sequential Stern-Gerlach measurements that we have considered in the first three classes and so second and third classes. Okay, and then we will bring the ideas from this sequential Stern-Gerlach experiments. We look at the results of the experiments and then we will apply these ideas, the ideas regarding the probability of getting a particular result, ideas regarding how to construct an operator in terms of its eigenkets. Okay, using these ideas and orthogonality, etc. Using these ideas we construct different eigenkets and operators from that experiments, okay, from the physical quantities that we considered in that experiment, that is quantities like Sz, z component of spin, x component of spin, y component of spin. These operators we can construct. Already z component of spin operator we have constructed in one of the previous classes, and the its eigenkets sz plus and sz minus we have used as the base kits. Okay, and now what is remaining is we look at the operators sx and sy, and also the eigenkets sx plus minus and sy plus minus, how to construct them using these ideas. So we are going to do that.
So our aim here is to construct this sx plus state, sx minus state, similarly sy plus state and sy minus state as a linear combination of these base states sz plus and sz minus. So we have used a shorthand notation for sz plus, simply ket plus. Similarly, ket sz minus is simply ket minus. So we choose these two as the base kits of the two-dimensional vector space, and such states sx plus, sx minus, sy plus, sy minus, etc. we need to construct in terms of the base kits. That's one thing. And secondly, these operators sz, sx, sy, etc. we can try to construct, okay, in terms of the base kits. So that is our plan. So for this we will be using all the results that we have obtained so far. Okay, so let us look at here. Let's look at this part, the third part of the sequential measurements. The input is sx plus. Okay. Now the output, what is, let's say some at this stage some 500 particles are here, and what you get in the output is 50% of the particles are. That means what you see here is you have two beams. Okay, one corresponding to sz equal to plus h cross by 2, the other corresponding to sz equal to minus h cross by 2, and these two beams are of equal intensity. Equal intensity. So equal intensity means the probability of getting these probability of getting a particle in this beam, probability of finding a particle in this beam is equal to that in this beam. Probability is the same. Okay, total probability has to be 1, so that means the probability of particles to be found in each beam, or probability for particle to be in the state ket plus and ket minus are 50%. That means 1 by 2. Okay, so from the experimental observation that the two beams are of equal intensity, we can conclude that these two beams are having equal probabilities to be in this state. Okay, that means 50-50, that means 1 by 2. Okay, so what is the so what you get here is the probability of getting plus or minus h cross by 2 is 1 by 2, right? Either plus h cross by 2 or minus h cross by 2 as the eigenvalue is 1 by 2. Okay, so let us start from there. So first of all, let us write down the equation for what is the probability of getting plus h cross by 2 as the eigenvalue. This is the final state, this is the initial state. So what is the probability? Remember that you have to take the inner product between final state on the bra vector side, initial state on the ket vector side, and take the square of that inner product. That is the probability. So we can say bra vector ket plus, this is the initial state, this is the final state, right? So sx plus square is equal to 1 by 2. Probability is half. Similarly, we can say for next one also we can say this one also. The final state is ket minus, so that you have to take as the bra vector side. Initial state is this one, sx plus, okay, modulus square is 1 by 2. Okay. So where do you get this? From this? Okay. Where do you get this? By observing that the two beams are of equal intensity. So probability is 1 by 2. So what can we say about this expansion coefficient? This is the square of the expansion coefficient. So what can be this expansion coefficient? Remember that in general this can be complex. So let us introduce when you consider this quantity, that is vector plus Sx plus. What is this quantity? This is the expansion coefficient. So we can introduce a phase factor here. So it is if it's a real number, then if you take the square root, it is plus or minus 1 by root 2. But we can introduce a phase factor here. We can write like this: e raised to I, let us say theta 1 into 1 by root 2. Okay. Again, you calculate this quantity back. This is given by this into its complex conjugate, that is this into its complex conjugate, which is e raised to minus I theta 1 1 by root 2. E raised to plus I theta 1 and e raised to minus I theta 1 will cancel, we get 1 by 2 again. So by introducing a phase factor here, there is no change in the observable result that the two beams are of equal intensity, okay, or each beam has a probability of 50%. Okay, so we can introduce a phase factor here. Similarly for this one, minus Sx plus is e raised to I, let us say theta 1 into 1 by root 2. So this is the expansion coefficient, this is also the expansion coefficient. Then what is this is our general state. General state can be expressed in terms of these two base kets, okay, with proper expansion coefficient. So let us write, so ket Sx plus we can write as okay, this is C1 times ket plus C2 times ket minus. So we have e raised to I theta 1 1 by root 2 times ket plus e raised to I theta 1 1 by root 2 times ket minus. Okay, so let me try to write it down in another way, in a different way. So let me take e raised to I theta 1 outside. So we have e raised to I theta 1 1 by root 2 plus e raised to I, so we have theta 1 minus theta 1 here, 1 by root 2 ket minus. Correct? Now this is called, this e raised to I theta 1 is called overall phase factor, because it is applicable for this ket plus and ket minus equally. Whereas this one, theta 1 minus theta 1 is called relative phase factor. Okay, because it is the difference, this is the difference in phase factor between ket minus and ket plus, between the two base kets or two eigenkets. This overall phase factor does not make any difference to the state ket, okay, general ket. Only this relative phase factor makes any difference. So let us ignore this overall phase factor. We can rewrite this expression like this. We can ignore this. Okay. And let me put this one. Let us say theta 1 minus theta 1 is equal to some delta 1. Okay. So then this expression will be e raised to I delta 1 times 1 by root 2 ket minus 1. Okay. Another way of saying is you can choose theta 1 as 0, then theta 1 is equal to delta 1. Okay. But then also, if theta 1 is 0 and theta 1 is equal to delta 1, then also this delta 1 is the difference in phases between theta 1 and theta 1. Theta 1 minus theta 1, or the other way, theta 1 minus theta 1. So it's a relative phase factor. Okay, if this is chosen as 0, whatever appears here is this with respect to this starting point. Okay, so it's a relative value, it's a relative phase factor. Okay, so this is the expression for Sx plus. Okay, Now similarly we have to construct Sx minus. For that let us come back to here. Suppose we do this experiment, the input beam is this. Okay, if the input beam is this, then the output will be the same, 50% intensity or equal intensity. Okay, that means the probability is 50%. That means we can repeat this argument with Sx minus. Okay, here then we will end up with a similar result here for Sx minus. Okay, so what do you let me write Sx minus as 1 by root 2 ket plus e raised to I, let me say eta 1, this is something like delta 1. Let us say another relative phase factor. So this is the relative phase factor will be ket plus and ket minus in this case. 1 by root 2 ket minus. Okay. But Sx plus and Sx minus are not independent completely, because there is an orthogonality relationship between them. Okay, Sx plus and Sx minus are eigenkets of Sx operator, so they are orthogonal, mutually orthogonal. So let us consider the orthogonality and then let us see how does it make any difference here. So this state and this state are orthogonal to each other because they are eigenkets of the operator Sx. So this is the orthogonality condition. Sx minus, inner product of Sx minus with Sx plus is 0. Okay, so let us substitute this. So this is ket Sx minus. So what is the bra vector? You have to take the adjoint of each term. Adjoint of this term is, so the bra vector side is adjoint of this term is 1 by root 2. Okay, this is real, so there is no need to take complex conjugate, and it's this ket vector will become bra vector plus. And here you have to take the complex conjugate of this scalar. So this will become e raised to minus I theta 1, so plus e raised to minus I theta 1 by root 2, and this ket will become bra vector minus. Okay, this is on the bra vector side. On the ket vector side you have this, so 1 by root 2 ket plus e raised to I delta 1 by root 2 ket minus. This is equal to 0. Okay, so let us expand it. So first this into this. Okay, so we have 1 by 2 ket plus bra vector plus times ket vector plus. Then next is this into this. Okay, then what you get is inner product between ket plus and ket minus. Ket plus and ket minus are mutually orthogonal, so that will be 0. Then here this into this, again you have ket minus into ket plus, that will be 0, and finally this into this. Okay, so what is it? This into this plus e raised to I delta L minus eta delta 1 minus eta 1. Okay, 1 by root 2 into 1 by root 2 is 1 by 2 minus ket minus bra vector minus ket vector minus. This is equal to 0. And this ket plus bra vector plus ket vector plus, this is 1 because ket plus is a normalized state. Similarly this is also 1. This is normalized. Okay, so we have okay, we can take 1 by 2 outside. So 1 by 2 into 1 plus e raised to I delta 1 minus eta 1 is equal to 0. Then the term in the square bracket must be 0. Okay, so what you get is, you can take this 1 to the right side. So we have this implies e raised to I delta 1 minus eta 1 is equal to minus 1. Okay, so what from this we can get that this left hand side I can write as e raised to I delta 1 divided by e raised to I theta 1. okay, which is equal to -1. So we can conclude that e raised to I theta 1 is equal to minus e raised to I delta 1. From here. That means this theta 1 and since these two are not mutually independent, there is because there is a constraint relation between them. It means that this eta 1 and when I say that they are not mutually independent, what I mean is it doesn't mean that they are linearly related. They are linearly independent, okay? But there is a constraint relationship between them. So that means there is a relationship between delta 1 and eta 1. This is the relationship. E raised to I eta 1 is equal to e raised to minus I delta 1. So in this position here, I can write, there is a minus sign, minus, instead of e raised to I theta 1, I can write minus e raised to I delta 1. So we have constructed ket Sx plus and ket Sx minus. So we have obtained these two kets, okay, and these are the eigenkets of the operator Sx. So once we have the expression for these eigenkets, then we can construct the operator Sx. So the operator Sx is equal to, in general, how do we construct an operator in terms of its eigenkets? It is summed over, summation over, take each eigenvalue, then multiply with the projection operator in terms of those eigenkets. Okay, then next eigenvalue, then the projection operator, like that. So we have only two eigenvalues here. What are the eigenvalues of Sx plus h cross by 2 and minus h cross by 2? So take each eigenvalue. The eigenvalue corresponding to this state is plus h cross by 2. Eigenvalue corresponding to this state is minus h cross by 2. So Sx operator is plus h cross by 2 into projection operator constructed from this eigenket. Okay, that is bra vector Sx plus, ket vector Sx plus bra vector Sx plus. Okay. Then consider the next eigenvalue, which is minus h cross by 2 corresponding to this eigenket. Okay. Then you construct a projection operator from this eigenket, that is ket Sx minus bra vector Sx minus. So this is the structure of Sx operator. Now we have to substitute ket Sx plus and bra vector Sx plus, similarly ket Sx minus and bra vector Sx minus. Okay, you can try that substitution and do the algebra. And the final result is, so you have to use the condition that this ket plus and ket minus are orthogonal to each other. Ket plus and ket plus is normalized, ket minus is normalized. Okay, and the final okay, this orthogonality and the normalization you may not use here because it will appear in the form of projection operator. Okay, but some terms will cancel, and the final expression for Sx is h cross by 2 if I take outside, e raised to minus I delta 1 ket plus bra vector minus plus e raised to I delta 1 ket minus bra vector plus. This is Sx operator. Okay. So you have to verify this part. You can check that Sx dagger is equal to Sx. If you take Sx dagger, then that means adjoint, then this will become plus, but then this ket will become bra vector and bra vector will become ket vector. That means you will get this term. Okay, this ket will become bra vector, this bra vector will become ket vector, and this will become its converse conjugate. So this term will turn to this one and this term will turn to this one. So we get Sx dagger is same as Sx, that is, it's a Hermitian operator. Okay, that you can verify. So what we have done is we have considered sequential Stern-Gerlach experiment, and from the data, from the observation, from the empirical data, we constructed Sx plus, ket Sx plus, ket Sx minus, and also the operator Sx. Okay, all these in terms of the base kets, ket plus and ket minus. Okay. Now consider the same sequential Stern-Gerlach experiment. This time you, in the second stage, you replace Sx by Sy. Okay, so first you measure Sz, then you measure Sy, and then again you measure Sz. Then what is the result? Let us look at that experiment. This time in the second stage, instead of earlier we measured Sx here. Now let us measure Sy. The input is ket plus. If you measure Sy, nearly 50% particle is in Sy plus state and the other 50% in Sy minus state. Now block this Sy minus state apart. Take this beam Sy plus state and again measure Sz. So again 50% particle will be in ket plus state and 50% of this one. Okay. So if there are 1000 particles here, 500 and 500 particles will be here nearly. And if you input this beam, then nearly 250 particles will be in ket plus state and 250 particles will be in ket minus state of equal intensity. How do we know nearly equal particles are there? Because the intensity of the beams are intensities are same. Okay, so it means that the number of particles will be the same. So the probability is 50%, we can say. So now it means that the probability of getting this ket plus state from this input state, when the initial state is this, the probability of getting this final state is 1 by 2, 50%. When the initial state is this, probability of getting this final state is also 1 by 2. So we can repeat all the arguments that we have done, we have followed in constructing these kets and this operator. Okay, the eigenkets and this operator. We can follow all these arguments and we can construct these two eigenkets and the operator Sy. Okay, just like this. So the results are identical. Only thing is that instead of this phase factor, we will have another phase factor because it's a different ket. So the results are Sy plus minus. And the eigenkets will be exactly like this with a different phase factor, 1 by root 2 ket plus, plus minus, plus stands for Sy plus and minus stands for Sy minus. Okay, e raised to I delta 2, a different phase factor, 1 by root 2 ket minus. Okay, these are the eigenkets and the operator Sy is h cross by 2 e raised to minus I delta 2. Okay, ket plus the vector minus plus e raised to I delta 2 minus plus. Okay, so we have we can construct the kets, the two eigenkets and the operator Sy. Now we can ask the question, is there any relationship between this delta 1 and delta 2? Okay, is there any constraint relation between them? Are they connected, these two states? Sx plus minus, Sy plus minus, are they connected in some way? Okay, in fact there is a connection, there is a relationship between delta 1 and delta 2. To understand that, let us consider another set of another sequential Stern-Gerlach experiment. Okay, consider this Stern-Gerlach experiment. A beam is moving in the z direction and first we are measuring Sx. Okay, then half the particles are in Sx plus state and half in Sx minus state. Then we take Sx plus state and then measure Sy. Okay, spin component in the y direction. So half of them, suppose there are 2000 particles here, nearly 1000 here and 1000 here, and half of this 1000 particles, nearly 500 particles will be in Sy plus state, the other 500 particles will be in Sy minus state. Okay, so we get this type of a result. What does it mean? It means that if the initial state is Sx plus, okay, then you get two beams of equal intensity here. That means the probability of finding a particle in this beam is 50%, here also 50%. So if the initial state is Sx plus, the probability of getting x plus h cross by 2 is 1 by 2. Okay. Similarly, probability of getting minus h cross by 2 is also 1 by 2. So we can use that relationship. Okay, that means how do you calculate the probability of getting plus h cross by 2? You take this final state, take the inner product with this initial state, take the square. Okay, so let us see. So what you get is Sy, final state is Sy plus, initial state is Sx plus, okay, square is equal to 1 by 2. Okay, similarly if you take the inner product with this and this also, then you get 1 by 2. Okay, so okay, I can put a plus minus here. So here we have considered the probability of getting this state and similarly probability of getting this state. Okay, the two situations. Similarly, if you take initial state as this one, then also you will get the same result. Okay, so let us consider only one of them. Okay, so let us proceed. We can substitute for Sy plus minus, we can substitute this one, and for Sx plus we can substitute the plus part. Okay, the top symbol, right? And if you substitute it and rearrange, after some algebra, what you get is okay. So what you get is 1 plus or minus e raised to I delta 1 minus delta 2, because in Sy plus minus you have e raised to I delta 2. In Sx plus you have e raised to I delta 1. So there is a connection between them. Okay, mod square is equal to 1 by 2. Now this is equal to 2. Okay, this is equal to 2. You get this result. Okay. So let us proceed further. Our aim is to get a relationship between delta 1 and delta 2. Okay, let us see. So how do you proceed? So this mod square means there is a complex quantity here. So mod square means you have to take the complex number multiplied by complex conjugate, right? So what is the value here? 1 plus minus e raised to I delta 1 minus delta 2 into 1 plus minus e raised to minus I delta 1 minus delta 2, right? This is equal to 2. Okay. Now we have to expand this. Okay, let's expand it here. So we have 1 into 1, 1. Then 1 into this one, we get plus or minus e raised to I, e raised to minus I, okay, delta 1 minus delta 2. Then this one into this one, okay, so we get again plus or minus e raised to I, delta 1 minus delta 2. Then this into this, okay, that will be 1, so plus 1. Okay, this is equal to 2. So we have 1 plus 1, 2, then plus minus. Okay, this is like e raised to minus I theta plus e raised to I theta. So e raised to minus I theta is cos theta minus I sin theta. E raised to I theta is cos theta plus I sin theta. So that I sin theta part will cancel. We get 2 cos theta. So that is 2 cos delta 1 minus delta 2 is equal to 2. So the 2 will cancel. So we get 1 plus or minus cos delta 1 minus delta 2 is equal to 1, right? Okay, so 1 plus or minus cos delta 1 minus delta 2 is equal to 1. So we have cos delta 1 minus delta 2 must be 0, which means delta 1 minus delta 2 is plus or minus pi by 2. Okay, so there is a connection between this delta 1 and delta 2. Delta 1 minus delta 2 is plus or minus pi by 2. I have summarized the results here. These are the previous results that we have obtained, and now we have got delta 1 minus delta 2 equal to plus or minus pi by 2. And what it means is that if you look at the matrix elements of or the operator Sx and Sy, okay, it means that if the difference is plus or minus pi by 2, then it means that some of the matrix elements in the operator Sx and Sy can be imaginary. Okay, some can be real, some can be imaginary. If we choose Sx to be real, then Sy will be purely imaginary. Okay. On the other hand, if we choose Sy to be real, then Sx will be purely imaginary. Let us see how it is. A convenient choice here is, let us put delta Sx as real. Not to make Sx real, what we can do, we can put delta 1 is equal to 0. Okay, if delta 1 is equal to 0, this is 1, then Sx contains only real matrix elements. Then what about delta 2? Difference should be plus or minus pi by 2. So if delta 1 is 0, delta 2 is plus or minus pi by 2. Okay. Now we can have two choices, and these two choices of delta 2 correspond to right-handed coordinate system and left-handed coordinate system. And if you are using right-handed coordinate system, then the correct choice is delta 2 is equal to plus pi by 2. Okay, let us see what happens when we make this choice. Putting delta 1 equal to 0, okay, here it is 1, okay, here also it is 1. So this is Sx now. Similarly, Sx plus minus becomes, we get, this is 1, okay, so we have plus minus 1 by root 2, okay. So there are no complex coefficients here and here, okay, no matrix element is complex. I mean, all the matrix elements are real in Sx. Here also expansion coefficients are real. But what about Sy, operator Sy? Now delta 2 is plus pi by 2. Then if delta 2 is pi by 2, you have e raised to minus I pi by 2, which is cos pi by 2 minus I sin pi by 2, which is minus I. Okay, so this is minus I times ket plus the vector minus, here e raised to I pi by 2, which is plus I. So we can see that all the matrix elements of Sy operator are purely imaginary. If you choose Sx to be real, Sy will be purely imaginary. What about this state? Here also we have e raised to I pi by 2 is plus I, right? So we have for Sy plus minus, we have 1 by root 2 ket plus minus I by root 2 minus. Plus stands for Sy plus, minus stands for Sy minus. Okay. So for this choice we have this one. We can have other choices also. Okay, we can have both delta 1 and delta 2. Delta 2 can be chosen as 0, then delta 1 will be pi by 2. In between also we can choose. Okay, for other choices, then there will be imaginary terms in both Sx and Sy. Okay, and there will be complex coefficient for both Sx states and Sy states. Okay, so we have constructed, we started with this sequential Stern-Gerlach measurements, and we have constructed now Sx states, Sx operator, Sy states, Sy operator. Okay, for that we have used the idea of the postulates of quantum mechanics. The result of each individual measurement will be one of the eigenvalues, and what is the probability of getting a particular eigenvalue as the result of an individual measurement, and then what is the expectation value. Okay, we have used the idea of probability here basically. and how to construct an operator in terms of the eigengets. These ideas we have applied here. So this is an illustration of whatever we have, whatever postulates we have been using so far. Okay, and also this discussion shows that these complex numbers are essential features of the mathematical structure of quantum mechanics. Okay, this expression for Sx plus minus and Sy plus minus. In the first 2-3 classes on sequential Stern-Gerlach experiments, maybe the third class we have arrived at this, we have conjectured these expressions by comparison with the circularly polarized light. Okay. Now here we have no such analogy we have made. We have completely considered only the sequential Stern-Gerlach experiments. Okay, and we have used the idea of the probability of getting a particular eigenvalue as the result of measurement. Only that idea we have mainly used. And now we see that these complex numbers are emerging naturally as the mathematical structure of quantum mechanics. Okay, so that concludes our discussion on the quantum measurement in a system.